Hello everyone, welcome to this particular module. So in this particular module, we will talk about a very important concept in statistics that is known as central limit theorem. Now, central limit theorem seems very difficult to most of the students, but the concept and the application is very easy. So in this particular module, we will focus on central limit theorem. So that's the ultimate goal of this module. But to reach that particular goal, we need to also understand a few more concepts. So we'll start our discussion with what is probability distribution. We will talk about z-score, normal distribution, inferential statistics, and finally, we will combine everything to learn central limit theorem. So let's get started. Now, the very first thing that we will talk about is what is your probability distribution. So let me take one example. Now, when you roll a dice, roll of a dice. So when you roll a dice, the sample space, basically the output that you can get is 1, 2, 3, 4, 5, or 6, right? I'm talking about a fair dice. Now, if I ask you, what is the probability to get 1? Basically, when you roll a die, what is the probability that you will get the number 1 as the face of the die? And you can simply answer it as 1 divided by 6. And this probability is same for getting 2, getting 3, getting 4, getting 5, even getting 6, right? Now, these are known as your empirical probabilities, or these are basically theoretical, right? But this is not going to happen in reality. So if I actually conduct experiment, so let's do one thing. Let's roll the dice and let's write down the numbers which we get. So I already have one simulator where if I press roll, I will get the particular output. So right now it is 4, 5, 1, 5, 4, 5, 1, 5. So let's write it down. So 4, 5, 1, 5, and then 2, 4, 6, 6, 4. So 2, 4, 6, 6, 4. Let's do one more time. 1, 5, 3, 6, 4. 1, 5, 3, 6, 4. So 1, 5, 3, 6, and 4. Now, if you see, the numbers that we have obtained is not exactly 1 by 6. So let's create a quick table with the outcome or output and the probability of that output. Now let's write 1, 2, 3, 4, 5, and 6. Now 1 has appeared for 1, 2 times. And how many times we have actually executed or rolled the die? So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So here I'll get the output as 2 times divided by 14. Then how many times I have obtained 2? So 1, only 1 time, right? So 1 divided by 14. Then 3, 1 time. So 1 divided by 14. 4, 1, 2, 3, 4 times. 4 divided by 14. Then 5, 1, 2, 3, 3 times. And 6, 1, 2, 3. Again, 3 divided by 14. Now these are known as your experimental probabilities. These are known as experimental probabilities. Basically, those values or those probability values that you get as the output when you actually perform the experiment. Now, you guys must be thinking why this is not exactly 1 by 6. Now, this is known as basically the law of large numbers. So, what it states, law of large numbers. Basically, if you do this experiment for infinite number of times or very large number of times, so when the experiment is performed for very large number of times, and there is no correct value that I can tell you for n, which is how many times I should perform this experiment. So this n is again very large, which does not have any number. I can say it is infinite. So when you perform this experiment infinitely, then your experimental probabilities will approximately or will closely reach to your theoretical probabilities. And I can show you this, though there is a very good website that can help you understand this. So there is a website known as Brown something. Let me just see. Brown statistics. Brown statistics. Experimental learning. I'm not sure, but so I'm getting brown. Okay, let's do one thing. Statistics learning with animation. Okay, so I need to pause this video because I need to search it. So give me 1 minute. I'll quickly resume. Okay, so guys, I was talking about this particular website, and let me show you. So here what you see are the true probabilities. But if I flip the coin, I can see that once I flip the coin for 1 time, the probability for tail is 1 by 1 because I obtained a tail. If I flip it again I got a tail, so it is 2 by 2. What if I flip the coin for 100 times? Now you can see that it is approximately 0.52 and 0.48. So it is not exactly 0.5 and 0.5. If I flip it again for 100 times, now you can see it is very close to 0.5, right? So this is what law of large number is. The more number of times you perform the experiment, the chances of getting the experiment probability is equivalent or close to the theoretical probabilities increases. And that's what I was talking about here. So here, the particular output that we are getting is not same as 1/6 is because these are experimental probabilities and they might become close to 1/6 once we perform this experiment for many times or infinite number of times. Now we were talking about probability distribution. So what exactly that mean? Now, if I plot this, so let's plot this. So I will keep the output over here and the probability over here. So 1, 2. The probability of getting 1 is 2/14. So let's say this is 2, this is 3, this is 4, this is 5, and so on. And this is 2/14, this is 3/14, 4/14, and 5/14. At 1, I got 2/14. So let's put a block over here. At 2, we got 1/14. Then at 3, also 1/14. Then at 4, it is 4/14. Then at 5, it is 3/14. And again, 3/14. So this is basically known as probability distribution. Probability distribution. Basically, when I plot the probabilities in a graphical representation, it becomes probability distribution. Now, this probability distribution is discrete. Discrete. Why? Because here, the output is discrete, or output of the experiment. Output, 1 second. So, output of the experiment is discrete. And what is the experiment? Roll of a dice. But we can also have continuous probability distribution also. Now, let's talk about continuous probability distribution. Basically, let's say, so when the outcome of the experiment can take continuous values, then we will get what is known as your continuous probability distribution. Now, let's talk about such experiment where the outcome can take continuous value. So let's say the experiment is, I ask you to predict the time I will take to reach my home from office. So that is which is known as the commute time. So the experiment is commute time. Now, let's say I usually take 10 minutes to, let's say 30 minutes. So minimum is 10, maximum is 30. Let's assume. Now, let's say on day 1, I took 12 minutes. In day 2, I took 12.5 minutes. In day 3, I took 13 minutes. In day 4, I took 19 minutes. Day 5, I took 28 minutes, and so on. Now, I want to represent this information in a probability distribution. So what is a probability? Again, there are possibilities that between 12 to 13, there are infinitely number of possibilities, right? So maybe I can take 12.22 minutes, 12.12 minutes, 12.23 minutes, so infinite, right? So what I'll do, instead of taking value as 12, I'll take the bucket and then the probability. So what are the buckets which are possible? So let's say I'm taking a bucket which is between 10 minutes to 15 minutes, 15 to 20, 20 to 25, 25 to 30. And now I will put the number of times I have taken time in this bucket. So let's say it is 5/15. Here it is 2/15, 3/15, and again 5/15. No, 5/50. Okay. Now if I want to plot this information, again I will keep bucket on x-axis, probability on the y-axis. It will be 10, 15, 20, 25, and 30. Now when I plot this, also let's put 2, 3, 4, and 5 over here. Now when I plot this, I will not leave a gap in between what I have done over in the discrete probability distribution. So it is 5/15 between 10 to 15. So I'll take this block and plot it like this. Let me just correct it. Like this. Then 2/15. So like this. Then 3/15. Like this. And then again 5/15. So like this. Now this is your continuous probability distribution. This is your continuous probability distribution. So basically this helps us to understand where we have more chances. So as you can see that most of the chances of me taking commute time is in the lower and the higher side. So most of the time I'm either taking between 10 to 15 minutes or I'm taking 25 to 30 minutes. So either on the lower side or on the higher side. Now if I show you this particular graph, you can easily tell me that the probability of me taking less time or more time is higher compared to me taking the middle time, either 15 to 25 minutes. So this is basically your probability distribution. Now let's try to understand how this is helpful to understand normal distribution. So one of a kind of distribution is normal distribution, which is yet another probability distribution, but it comes with a lot of properties. So that we will talk about. Now let's try to understand what is normal distribution. Before I teach you about normal distribution, we need to understand one very important concept which is known as z-score or z-value or z-value. Now let's try to understand what is z-score or z-value. If you think about just the definition, it is basically the number of standard deviations from the mean or average. So when I represent a value in the number of standard deviations from the average, it's basically your z-score. The formula to find out the z value is given as x minus mean divided by sigma, which is basically your standard deviation. And what is the advantage of this, or maybe why we need to learn z-score? Let's try to first of all see one very important example. So what I'll do, I'll quickly take you to a very important example which I have here for you. Now here you can see we have age, we have cholesterol, we have blood pressure, and all these three columns are in three different scale. So when we talk about age, it is in years. BP's has some unit, cholesterol has some unit which I don't know. Now I am not able to understand how large or how small this value is, because number one, these three values are in three different scales. So let me do one thing. Let me just quickly copy this in a new sheet. And now here I am not able to understand whether this is high or low. So I know, because see, we all can interpret age, right? 50 year is a high number because generally we human can live for 80, 85, or maybe 90, or maybe 100. But 50 is considered to be a higher number, whereas 20, 30 is considered to be a lower number. So we know the range. But what about BP? We as a technology students, maybe I'm not aware about BP. What is the unit of BP? Similarly, I'm not aware about cholesterol. So these values are non-interpretable. Also, when I give this particular data to a computer or a machine, now since machine considers everything in one common scale, it will consider this as 70 is lower than 130, 130 is lower than 322. So there are two problems. Number one, I'm not able to interpret because I don't know the unit. Number two is if I give this data to computer will consider all these values in one common scale, which is minimum 0, maximum is some infinite value. In order to solve these two problems, what I do is I will convert the scale of this data to one common scale, which is also known as the process of scaling. Think of this particular scaling concept as converting meter to centimeter or kg to gram. This is exactly what we are going to do. So what I'll do now is I'll quickly calculate. So let's calculate average. Okay. Let's calculate standard deviation. Okay. And here, let me delete this one. I don't need. Here I will calculate for, so average of the entire column. Then I will just expand it over here. So this is average of PP and this is average of cholesterol. Similarly, the standard deviation of this column. Oh my God, what happened? So let me just correct this now. Is equal to standard deviation of this column. And I will do the same thing. Again, I'll expand it over here. Now I'll just copy these column headers, put it over here, and we'll name this as Z, Z, and Z. Now I'll apply the formula is equal to X, which is this value. So I'll initiate a bracket. X minus mean. I don't want this value to change when I expand the formula. So I'll just freeze these two values. Mean divided by standard deviation. Again, I don't want to change this. So I'll freeze this. Also, I'll not freeze this. And yes, let's run it. So let's expand this. I will expand it over here and I will expand it. Now let's try to read a value. What is the meaning of this 1.3? This 1.3 basically mean, or let's start with this 1.7. This mean that the age of this person is 1.7 standard deviation above average. Now, if you want to read it, you have to think in such way. So here we have a line, here we have 0, which is the mean of the data. And here we have 1, we have 2, we have 3, and so on. Here we have -1, -2, -3, and so on. Now, basically, your Z, this is known as a Z scale, where the mean of the data will become 0 and the standard deviation will become 1. So your Z scale will have mean of 0, standard deviation of 1. And this value, so basically, let's say if I have a value, let's say 22, now I will represent this value in Z scale, and that would become, let's say it became plus 1.5. So this value would be somewhere about here. So this means that this value is 1.5 standard deviation above mean. Similarly, if the value is -1.5, that means that value is 1.5 standard deviation below mean. Now, this is what you have to keep in mind, that we have a number line. In middle, we have a 0, that is the mean of the data. We have positive numbers, we have negative numbers, positive number representing the number of standard deviation above mean, and negative numbers representing number of standard deviations below mean. And I am now converting each value in this scale, So let's see. So here 1.7 mean. So let me draw the scale over here also. Let's say we have 0 over here, -1 over here, -2 over here, +1 over here, and 2 over here. Let me just color this. So I will center it. I will add a border, and we'll also put a color. So for 0, I will put a color as yellow. For this, I'll put a color as red, and this one as green. I'm just randomly putting a color just to help you guys understand that this is a scale. Now, 1.7 will lie somewhere over here, right? Between 1 and 2. So this person has an age which is above average, and it is 1.7 standard deviations above average. Now this person age is 1.3, this person age is 0.2. So this person age is very close to the average age. Now this person age is -1.14. So this person age is below average, and it is 1 standard deviation below average. Like this, you can now read all the columns because now you know the scale. Now you know whether the value is high or low. So here, if you read this value, you can easily say that this person has a cholesterol level which is very high. It is 6 units or 6 standard deviations above average. It is very high, right? Now, but if I show you this value, which is 564, and if you don't know the scale of cholesterol, you cannot determine whether this value is high or low, right? So this is a problem, and this is how Z scale or Z score gets you a solution. One more advantage is now if I provide this data to a machine, a computer, now since all the three columns are in one common scale, which is Z scale, my machine will now be able to measure them, will evaluate it in a same parameter, in a same benchmark, right? Previously, this was getting compared on a scale of 0 to infinite, but now it is in this scale. So now since all the three values are in one common scale, my machine will take a better decision. This is what the advantage of Z scale or Z score is. Now we will talk about how this concept can be helpful in normal distribution. So let's get started. Now let's talk about normal distribution. So normal distribution is your probability distribution. And this is basically the most studied and the most visible probability distribution which is between us or which is among us. You would have seen this kind of structure, right? So this is basically a normal distribution which appears to be a bell-shaped curve. Now, why I am saying this is naturally occurring or why I'm saying this is most studied? The reason is, number one, you will see normal distribution in most of the natural phenomena. For example, the income distribution. So income distribution will always follow this kind of distribution or normal distribution. Why? Because if you see this x-axis to be the income and y-axis to be the number of people or count of people, you will see that there will be most of the people are earning in the mid-range. So this is mid-range, with few earning very low income, and with few earning very high income, right? The similar concept or the similar ideation can also be seen for height, the height distribution in a country. You will see most of the people around the average height, which is basically this, considering this to be the average. So most of the people will around the average height, with few very tall and with few very short. So this is how the distribution of the height will also be there. Now, why I am saying that this is the most studied distribution? So in your basically in your research field, in statistic field, scientists were able to discover a lot of properties of this distribution that we will use in solving a variety of problems in data science and in data analytics. One of the properties, so I'll write second as the height distribution. So one of the property or one of the way you can identify this distribution to be a normal distribution is it will appear as a bell-shaped curve. Second is it is always symmetrical around mean. Symmetrical around mean or average. Basically, if I consider this to be the center point, so it will be symmetrical around this point. So half of your data will lie over here and half of the data will lie over here. So it's like a mirror image. It is symmetrical around the mean. The second point is that there's a rule known as 1, 2, 3 rule. And the rule states that your 68% of the observations will lie around mean plus minus 1 standard deviation. 95% will be around mean plus minus 2 standard deviation. And 99.7% will be around mean plus minus 3 standard deviation. So this is your property, basically 68%. This is known as 1, 2, 3 rule. Now this helps us to understand basically how much data I can expect in what range. And I will show you the proof of this also, but this is yet another property of normal distribution. So one property is it is symmetric around average. Second one is it holds the rule of 1, 2, 3. Again, one more very important clarification. These two properties will only hold true or exactly true when we get a perfect normal distribution. Now, when I say perfect, I basically mean this kind of distribution, which is looking exactly like a normal or exactly like a bell. But if your distribution is near normal, if the distribution is near to normal, then the properties will approximately hold true. Not exactly, but approximately it will hold true. Let me show you a proof to basically prove this particular 1, 2, 3 rule. So what I'll do, I'll go back to the same example. Now I'll take cholesterol, copy it, paste it to maybe over here. First of all, I will plot a histogram for it. So insert, chart, and then you can see this is a histogram. Now this histogram, let me do one thing. Let me go back. Let me plot it again. So insert, chart, and we have a histogram. Now this histogram is not perfectly normal, and you can see a tail over here, right? So it is not like a perfect symmetric bell-shaped curve, is because of this outlier value, which has taken the tail, the right tail, to extreme right. And again, this is not perfectly normal, but close to normal. That basically means this particular distribution will hold the 1, 2, 3 property, not exactly, but approximately. Let's test. Okay, let's test. So I will first of all find out the mean, or maybe let me write average and standard deviation. So is equal to average. I will choose this, and standard deviation, I'll choose this. Okay. Now let's find out the first range where the rule says that 68% of data will lie. So let's find out the min and the max. So is equal to mean minus 1 standard deviation is equal to mean plus 1 standard deviation. Now this is basically the range. I will apply the filter over here just to find out how many such values we have in this range. So between filter by condition is between 197.97 to 301.34. And let's click OK. Let's count. So we have, let's see over here, the count is 195. So I'll do one thing. I'll remove the filter. I will do one thing. I will say none. I'll say OK. So we have 195. So these are the count and this is total. So what are the total number of rows? Total number of rows are 270. So let's put 270 over here and let's put percentage. So this divided by this, which I'll convert into 100. So here the number is 72.2. Again, it is 68% over here, and here it is 72.2, because again, as I've told you that this is not perfectly normal, this is close to normal, and that is the reason this number and this number is close to each other, not exactly equal to each other. Let me just cross check everything, average and minus and plus. Okay, now 95%. So mean is equal to mean minus 2 times of standard deviation. Similarly, mean plus 2 times of standard deviation. So 146. So condition is between 146.28 to 353.03. Let's enter. Let's count. Now we have 261 values. Let me remove the filter. I'll write 261. Total is again 270. Let me expand this. It is 96.6. Again, very close to 95. Not exactly, again, because it is not perfectly normal. 99.7% will lie in 3 standard deviation. So is equal to, why we don't have mean? 1 second. Haven't we removed? None. Okay. So is equal to average minus 3 times of standard deviation and is equal to average plus 3 times of standard deviation. Oh my God, what I have done? 3 times of standard deviation. So let's count. Again, I will apply the filter is between 94.6 to 404.7. Let's click OK. Let's count. It's 266. So let's remove none. Okay. 266. Here again, we have 270 and the percentage is 98.52. Again, very similar, close to this, but not exactly. So what you guys are able to understand, these numbers are real, or I would say experimental number. These are after research work done by scientists on the various normal distributions that they have observed and studied, while these are for the normal distribution which we have observed. Now, the reason this is not exactly matching this is because number one, this data comes with outlier, so we do not have perfect normal. Second is the data is also very less. And that's the reason I cannot get these numbers to be exactly same as the experimental one. But this is one of the property that we use variety of times to learn the properties of any data, which is continuous, because we need continuous probability distribution. Now, let's try to understand how this particular technique can be helpful to solve a business problem. So I'll take a business problem, I'll try to understand how we can solve that business problem, or maybe a small question to help you understand the usage of this particular rule. Okay. Now let's try to solve this problem to understand the application of the property that we have learned, which is 1, 2, 3. The question says, the height of a people is normally distributed with a mean of 65 inches and standard deviation of 2.5. So your mean is 65 inches, standard deviation is 2.5 inches. What fraction of people whose height is between 60 to 72.5? Now, if I assume the heights are normally distributed, it should form a bell-shaped curve with mean as 65. Now, 60 will lie somewhere over here, and 72.5 will lie somewhere over here. Now, please focus on one important point, that is standard deviation is 2.5 inches. So this value is 1 standard deviation above average, and this value is 2 standard deviation below average, right? Now, if you recall the rule, which says your 68% of the data is between plus minus 1 standard deviation, that basically means if you try to divide it by 2, right? Because this is 1 standard deviation, and we know that normal distribution are symmetrical. So if 68% in total is in 1 standard deviation above and below mean, half of it will be on the either side. So this area is definitely going to be 32%. So my 32% data will lie over here, right? Now we also know that 95% data lies between plus minus 2 standard deviation. So I know that this value is 2 standard deviation below the mean. Again, if I divide it by 2, it will be how much? So your 45 is 90, and this is 5, so 2.5, so 47.5, right? So this is definitely going to be 47.5%. Now if I add, so from here I get 32, from here I get 47.5. What will be the answer? 4, 5, 6, 7, and 7, 8, 9.5. 79.5% of the people will be between this range. We can also do this, like we can also solve this problem using Python also. But if we want to use Python, we need to learn about the concept of cumulative distribution function. Now we will talk about it, but let's solve question number B also. So in B, what fraction of people are shorter than 67.5? Again, let me draw the normal distribution. We have 65 over here and shorter than 67.5. So 67.5 will be over here. 67.5. Now, I did a mistake or what? Is it 72? It is 62.5. I'm really sorry. This is 62.5. Also here. So here it is 67.5. No, this was 67.5 only. A mistake over here. So this one, it will be 67.5. Here also it will be 67.5. And this is 67.5. So this value is one standard deviation above mean. And the question is, what fraction of people are shorter than this? So basically, I need to find out the percentage from here all the way up to here. Now, what this value is, this is 32%, as we have calculated previously also. And as per the property of normal distribution, I know that this area will definitely be 0.5, which is 50%. So 50% plus 32.5, this will be 5, 6, 7, 8, 82.5%. Clear, everyone? So this is basically how you can manually solve. But there is a way to solve these questions using Python, where I'll be using the SciPy library. But there is one important thing that we have to learn, which is CDF, cumulative distribution function. Cumulative distribution function. In the case of cumulative distribution function, we are basically trying to find out the total probability till a point. For example, if I was asking you in the previous question, what is the probability that, so the question was, what's the probability that a height of a randomly selected person is below 67.5 inches. So basically, I'm talking about this area, the complete area till this point. Basically, I'm talking about the cumulative till this point. Cumulative. Okay. Now, this is known as CDF, cumulative distribution function. Basically, from this point all the way to this, we are adding all the probabilities. And till this point, my probability would be what we have found out, which is 0.825. In order to better understand CDF, I will take you back to this example. Let me just copy this and put it over here. So the CDF for this would be, so here it is 5 by 15 only. Here it will be 5 by 15 plus 2 by 15, 7 by 15. Here it will be 5 by 15, 2 by 15, 3 by 15, which is 10 by 15. And here it will be 15 by 15. So if I draw the cumulative distribution function, it will look like this. So again, 10, 15, 20, 25, 30. So here we have, let's say 5, 10, 15. So first of all, it is 5, then it is 7, then it is 10, and then it is 50. And after this, it will be 1 only, because that is the maximum probability. So this is your cumulative distribution function. Basically, in short, CDF provides you total probability till that point. Okay, that's what your CDF is. Let's try to understand CDF using Python now. So I'll quickly jump to the Python notebook. So this is basically my data that we are going to use. Now, let me find out the average height of, before that, let's plot. So I will be using ChatGPT or maybe Gemini over here to quickly write the code, but you can write it, type it. So I'll say plot the histogram with the PDF of height and weight in two different plots side by side using the data df. Let's run it. So let's execute this. So here you can see that height is perfectly normal, but here it is not exactly normal, the weight, but height is looking like a very good normal distribution. Let's find out the average height. So I'll find out the mean together with that. Let me preserve it in the variable m. I'll also find out the standard deviation, df height standard deviation. Let's print m and st. So your mean is 66.36, standard deviation is 3.84. Now let's say I want to answer this question. The question is, just let's put this. What percentage of people are below the height of, let's say 70. I'm just keeping it with a random number 70. Now how we will solve this? First of all, so 70 is over here. I need to find out the area or the probability till this point, from here all the way up to here. I will use the package which is SciPy. So from scipy.stats, import norm, and then norm.cdf. Now this takes input as your log to the value x is 70, log which is your mean m, and scale which is standard deviation. So these are the three inputs. Let's run it. So the value is 82.7, which is 82.7% of the people are between height of 70. What if I want to find it for, let's say, height of 60? So how many people are below 60? It is 84, or maybe it is just 4.8% people. But let's say if we want to find out what percentage of people are above the height of 70, how we can do this now? So let me just copy this, run it, and let me say above 80, above the height of 70. So all I will do is I'll just say 1 minus, because now I'm interested in this area. So total area is 1. So total area is 1. So 1 minus this below area will give you the top area. So I'll say 1 minus this, and we have 17.2% people. Okay. So this were the basics of how we use normal distribution. I hope you guys are clear with normal distribution, on the properties of normal distribution, how we can use it to solve a database question. We will proceed forward with inferential statistics. So let's proceed in the next video. Example I have here. Okay, before I tell you examples, let's say